Hello, and welcome to the BMC Learning Series. In this session, we'll cover an overview of MainView Batch Optimizer, otherwise known as MVBO. This is the introduction and first of a series of 3 courses on MVBO. So what does MainView Batch Optimizer do? Well, it reduces elapsed time for batch processing by removing embedded wait times. It reduces I/O wait time through efficient storage usage. MVBO runs jobs and job steps in parallel, so the jobs are not wasting time with serial processing. It exploits parallel sysplex. MainView Batch Optimizer includes Data Optimizer, Job Optimizer, and Job Optimizer pipes. Let's discuss each of these components in more detail. The Data Optimizer works with both VSAM and QSAM files. It is transparent to existing JCL and applications. Data Optimizer dynamically selects optimal buffer values and processing techniques based on current system resource usage. For example, it considers paging rate, CPU rate, below-the-line storage, among other things, when determining how to optimize batch processing. Specifically for QSAM flat files, Data Optimizer adjusts region sizes to improve storage management. It takes advantage of extended addressability to acquire resources without having an impact on existing batch jobs. All of the optimization is transparent to the application, so there's no need to make any JCL or program changes. VSAM data optimization utilizes various buffer strategies to achieve optimization. Data Optimizer chooses buffer values based on the access intent of each program for that file. An example, if a file is open with random intent, Data Optimizer establishes an LSR buffer pool and dynamically switches to LSR processing, which benefits random access patterns. However, if the access intent is sequential, the Data Optimizer sets up a buffer technique that is designed to benefit sequential processing. If the program includes both random and sequential processing, Data Optimizer starts with the LSR processing for random intent, captures history data, and then dynamically switches between the LSR and NSR processing as needed. Data Optimizer exploits VSAM options like deferred write and VSAM load mode processing to run processes more quickly and efficiently. For QSAM and BSAM flat files, the Data Optimizer builds special buffers above the line that allow pre-reading of large amounts of data, significantly reducing wait time for data to be returned to programs. Data Optimizer replaces low-level I/O processing, providing complete control of buffer management and physical I/O requests. All logical I/O requests from the application are satisfied by the product's internal buffer manager. For sequential processing, MVBO reads large amounts of data and overlaps I/Os to maximize performance regardless of blocking characteristics. And again, all of this processing is transparent to the application, so no JCL or program changes are required. MainView Batch Optimizer policies are sets of rules that are set to control how the product works in a particular environment. By setting policies, you get optimization that is transparent to existing programs. Sample policies are provided, and changes can be made through the ISPF interface. You can use DD overrides for testing and ad hoc changes. You can also use a user control exit for complex selection algorithms. Okay, let's look at a report that shows the difference that Data Optimizer made in one situation. A program was accessing a VSAM file and issued approximately 3.5 million reads and 3.5 million points. And we can see that this program used skip sequential processing. Without Data Optimizer, native VSAM processing would have resulted in over 10 million I/O operations to access the indices and data components of the file. With Data Optimizer in place, 2 physical index I/Os and 9 physical data I/Os were able to satisfy the requirements of this program. We've seen what data optimization can do, So now we'll look at job optimization. Job Optimizer builds on the benefits provided by the Data Optimizer by exploiting the parallel execution of jobs with a concept called step splitting. In other words, it runs multiple steps with no data dependencies in a single job in parallel, rather than in serial mode. Step-to-step piping enables parallel step execution when step 1 writes passes a file into step 2. A data pipe is simply a buffer in memory the data is written to. Because the reading program reads directly from the pipe, no I/O is required. When the writer step finishes, the reader step finishes. Job Optimizer splits job steps for piping and concurrent execution based on history and policy definitions that the user defines. Let's take a look at a batch job with and without job optimization. On the left, you see a 6-step job where each step runs serially. Step 1 writes a temporary file to DASD, Step 2 then reads the same file, and so on until the job completes. Each step must wait for the preceding step to end before the next one begins. On the right, you see the same job with job optimization. A user-defined job policy enables steps 1 and 2 to run at the same time. Step 1 runs on JES initiator, and step 2 runs on a spawned initiator called XJS initiator. Let's examine a concept called the pipe rule, which states that one can split going out of an update step, but not going into an update step. Step 3 shows the pipe rule in action. It serializes the step as well as step 4, even though the work is being done on a different LPAR. Job Optimizer established a pipe from step 5 to step 6 on a third LPAR. Step 5 reads the output from step 4, then pipes it to step 6. Parallel processing can significantly reduce elapsed time for batch processing. Here's another way to see the benefits of job optimization. This timeline shows the same job and highlights the time impact of parallel processing over serialized processing. In addition, the impact of Data Optimizer is shown as a reduction in the I/O requests. MainView Batch Optimizer takes the idea of parallel processing to another level with Job Optimizer pipes. Let's take a look. MVBO can establish pipes between a reader and a writer within a single job or externally to another job. We call it step-to-step piping when piping occurs within a single job. When data is piped outside of a job and into another job, we call it job-to-job piping. Job-to-job piping is a bit more invasive in your environment, as it requires you to make changes to the scheduler so that 2 or more jobs can run as co-requisite jobs instead of being serialized. With job-to-job piping, 2 jobs are on the initiators and running. It could be that step 5 in one job needs data from step 8 in the other job. When the jobs reach the steps that include pipes, they are held to obtain synchronization. MainView Batch Optimizer then establishes the pipes and starts piping. MVBO communicates directly with BMC Control-M to determine the nature of a piping collection and will ensure that all jobs within the collection will be submitted at the same time. Another example. Without piping, we find an extract program, such as a month-end processing that writes to a flat file. The file goes into a series of downstream processes and creates report 1, then report 2, and finally report 3. With pipes, the extract job pipes the data to all 3 downstream processes simultaneously. When the extract job finishes, the reports are finished, saving significant time. In summary, MainView Batch Optimizer provides comprehensive, intelligent, dynamic batch data and job optimization. It enables job steps and jobs to execute in parallel, dramatically reducing elapsed time for batch processing. In addition, MVBO balances batch jobs across Sysplex. That concludes the introductory course for MainView Batch Optimizer. For more videos on MainView and other BMC solutions, please visit our BMC Mainframe YouTube channel at youtube.com/user/BMC Software Mainframe/featured. That's it for this session. Thank you and see you next time.